Namaste and a very good evening to all of you. I welcome you to my channel, The Outlier. My name is Mithun. In today's video, I'll be talking about a very important theorem in statistics, which is called as the central limit theorem. Even before I proceed to demonstrate what exactly is the central limit theorem, when do we apply the central limit theorem, what are the different applications of central limit theorem, may I request you to subscribe to my channel, also like and share my videos. As far as the agenda of today's video is concerned, I have a five-fold agenda. Firstly, I'll be talking about what is the definition of the central limit theorem. The second important point which I'll cover is the three conditions for us to apply the central limit theorem. The third point is about the properties of the central limit theorem. The fourth point is the mathematical formula that can be used to express the central limit theorem. Last but not the least, I'll also be talking about some basic applications of central limit theorem. With this agenda, let's proceed to see what exactly is the central limit theorem. If you were to ask me to define the central limit theorem, I would define it as follows. Central limit theorem states that irrespective of the shape of the population distribution, I'll repeat, irrespective of the shape of the population distribution, the distribution of the sample mean will approximately be normal as the sample size becomes larger. There are three parts to this statement. The first part is when we are saying irrespective of the shape. What does this mean? This simply means that central limit theorem is telling us I don't care about the distribution of the population. The population could be Poisson, the population could be Bernoulli distribution or uniform or binomial or exponential. Central limit theorem says I care a damn about the distribution of the population. So that is the meaning of the first part of this statement, wherein we are saying irrespective of the shape of the population distribution, which simply means that we are not bothered, we are not concerned about the shape of the population distribution. Let me draw your attention to the second part of the statement, wherein we are talking about the distribution of the sample mean. Central limit theorem clearly states that the distribution of the sample mean will approximately be normal. This is the moot point in central limit theorem, that the distribution of the sample mean will be approximately normal. But there is a caveat here. What is that caveat? That caveat is expressed in the third part of the statement, wherein we are saying as the sample size becomes larger. Yes, the sample mean will approximately follow normal distribution, provided the sample size becomes larger, which automatically means that the sample mean will not be approximately normal for small sizes. So this is how we can state the central limit theorem in three parts. We begin by saying irrespective of the shape of the population distribution. Then we introduce the second part of the statement, wherein we are talking about the distribution of the sample mean, and we are making a very bold claim here by saying that the distribution of the sample mean will approximately be normal. There is a rider here, there is a heads up here, and that rider is that the sample size should be sufficiently large. In the subsequent slides, I'm going to break down these three parts in greater detail. This is the definition. If you do not have a statistics background and you feel that this is technically loaded, let me give you a simpler definition of central limit theorem. The alternative definition of central limit theorem is that for sample size of 30 or more, I repeat, for sample size of 30 or more, the sample mean is approximately normally distributed. I'll repeat this for you. Central limit theorem states that for sample size of 30 or more, the sample mean is approximately normally distributed. Let's look at the next slide. I know that this slide can be slightly intimidating. There are two pictures, one to the left side of your screen. The other picture is to the right side of the screen. By the way, I have picked up this particular image from Wikipedia. I'm quoting the source as well. So credit must be given where it is due. I have not personally created this particular picture. You can go to Wikipedia and use this particular picture as well. They've been kind enough to make this picture available. Now, there are two pictures that you're seeing. The one to the left side shows the distribution of the population. I repeat, the picture that you're seeing to the left side is talking about the population distribution. Please observe the shape of the curve. It is really crazy. It is definitely not normal. This curve that you're seeing to the left-hand side is not normal and it is asymmetrical. But this is the beauty behind the central limit theorem, which clearly states that we don't have to worry about the shape of the population distribution. It can have any shape. It can have any shape. The two parameters of the population distribution are the population mean and the population standard deviation. Remember, the population mean is indicated by using the symbol mu. This is a Greek notation called as mu. Similarly, the population standard deviation is shown using the symbol sigma. Now, from this population, if you were to take large samples and you were to calculate the mean values, and let's imagine that you plot the distribution of the sample means. What central limit theorem says is that the central limit theorem claims that when you plot the sampling distribution of the mean, you will get a beautiful bell-shaped curve. In other words, the distribution of the sample mean will follow normal distribution. So this is the main point. Please compare the shape on the left-hand side to the shape on the right-hand side. The shape on the left-hand side is not normal. The shape on the right-hand side is normal. So this is at the heart of the central limit theorem, wherein we are claiming that the sampling distribution of mean will be symmetric, approximately symmetric and approximately normally distributed. There are two additional points about the central limit theorem. The first is that when you take the mean will be equal to the population mean itself, which is mu. Please observe the mean to the left-hand side. It is mu, which is the population mean. The sampling distribution of the mean will also have a value which is equal to mu, or the population mean itself. Let me talk about the second point here. When you look at the standard deviation of the population distribution, it is indicated using sigma. Please observe the standard deviation of the sampling distribution of mean. The standard deviation is sigma by square root of n. So this is the second important point. The sampling distribution of mean will have a standard deviation which is equal to sigma by root n. I think this picture makes it crystal clear as to what central limit theorem claims. In the subsequent slides, let me explain central limit theorem in greater detail. Can we apply central limit theorem under all conditions? Let me ask this simple question. Can we apply central limit theorem under all conditions? The answer is no. We can't apply the central limit theorem under all conditions. There are certain prerequisites, there are certain conditions. If these conditions are satisfied, only then we can go ahead and apply the central limit theorem. There are primarily three conditions that you need to worry about when you apply the central limit theorem. What are these three conditions? The very first condition is that the sample size must be sufficiently large. I repeat, the sample size must be sufficiently large for you to apply the central limit theorem. What do we mean by sufficiently large? I'll explain this in the next slide. Look at the second prerequisite for us to apply the central limit theorem. The distribution must be independent and identically distributed random variables. So we can apply the central limit theorem provided we have IID random variables or independent and identically distributed random variables. Now, one question that you might ask me is, when can we claim that the random variables follow independent and identically distributed parameters? Usually, this condition is satisfied if the sampling is random. Remember, if the sampling is random, you will get independent and identically distributed random variables. If the sampling is not random, the second condition is violated. Let's now talk about the third and the most important condition, that is, the population distribution must have a finite variance. I repeat, the population distribution must have a finite variance. If it does not have finite variance, you cannot apply the central limit theorem. In other words, the central limit theorem doesn't apply to all those distributions with infinite variance. I repeat, the central limit theorem does not apply to all those distributions with infinite variance. A classic example of a distribution which has infinite variance would be the Cauchy distribution. Cauchy distribution has infinite variance. Remember that most distributions have finite variance. So to quickly summarize the prerequisites for you to apply central limit theorem, the first prerequisite is that the sample size must be sufficiently large. The second prerequisite is that you should have independent and identically distributed random variables. And the third prerequisite for you to apply the central limit theorem is that the distribution, the population distribution, must have finite variance. Let me now make a move on to the two important parameters here. The first is, what is the mean of the sample means? You can see here. Here, we are claiming that the mean of the sampling distribution is the mean of the population. You've already seen here in the couple of slides back, you've seen that the mean of the sampling distribution is the mean of the population. The second important point here is that the standard deviation of the sampling distribution is the standard deviation of the population divided by the square root of its sample size. I'll repeat this for you. The standard deviation of the sampling distribution is simply the standard deviation of the population divided by the square root of the sample size. Let's make a move on to the next slide. Here, I'm talking about what is the relationship between sample size and normality. This is a question which often people ask. How is sample size connected to normality? First of all, is there any relationship at all? Definitely, there is a relationship between sample size and normality, because sample size influences whether the distribution is normal or not. The first point that we need to keep in mind here is that the larger the sample size, the more closely the sampling distribution of the mean will be towards normal. So as the sample size increases, as the sample size becomes larger and larger and larger, the more closely the sampling distribution will follow a normal distribution. The second point here is, let's consider a different situation where the sample size is very, very small. If the sample size is very, very small, it is observed that the sampling distribution of mean is sometimes non-normal. Why is it non-normal? The reason being, the central limit theorem holds good only when the sample size is sufficiently large. Remember, this is a very, very crucial point, that the central limit theorem only holds good when the sample size is sufficiently large. I know that you might want to ask me this question as to what is the definition of sample size being sufficiently large. I'm going to answer this in the next question. What is the definition of large sample? Right? By and large, as a convention in the world of statistics, we consider a sample size of 30 and above 30 to be sufficiently large sample size. I repeat, if you have a sample size of 30 or greater than 30, you can go ahead and feel good and feel happy because you have a sufficiently large sample size. What happens when the sample size is smaller than 30? Then you can call such a sample as small sample. We can break down this statement into two parts, case 1 and case 2. In case 1, we are talking about when n is less than 30. N is nothing but a notation for sample size. When n is less than 30, the central limit theorem simply does not apply. There is no question of applying the central limit theorem for small samples. Why? Simply because the sampling distribution will follow a similar distribution to that of the population. Therefore, the sampling distribution will only be normal when the population is normal. Let's consider the second case when the sample size is greater than 30. When your sample size is greater than 30, what you're dealing with is a large sample. Here, the central limit theorem applies. When n is greater than 30, the sampling distribution will approximately follow normal distribution. So the big takeaway here is that we are trying to define what is a large sample. As a rule of thumb, as a convention, when n is greater than 30, you can say you have large sample, and when n is smaller than 30, you can say that you have a small sample. Let's make a move on to the next slide. Here, I'm talking about what is the relationship between sample size and standard deviation. In the previous slide, I spoke about what is the relationship between sample size and normality. Here, I'm going to speak about what is the relationship between sample size and standard deviation. Remember, there is an inverse relationship between sample size and standard deviation. Let me just explain this. But for those of you who are not familiar with the idea of standard deviation, remember the standard deviation is simply a measure of dispersion. It's a measure of variability or spread of the distribution. That is, how wide or narrow the distribution is. Let's consider two cases here. The first case is when the sample size is extremely low. Can you guess what happens to standard deviation for low sample sizes? When your sample size is very low, the standard deviation is very high. As I said, there's an inverse relationship. When sample size is low, the standard deviation is high. There's a lot of spread in the sample means because there aren't precise estimates of the population mean. Let's look at the second case. What happens when n is high? When the sample size is sufficiently high, you can see here the standard deviation is low because there's an inverse relationship between sample size and standard deviation. So these are two important points. When n is low, standard deviation is high. When n is high, standard deviation is low. Let's now go on to look at how can we mathematically express the central limit theorem. You can see here, mathematics at the end of the day is just a shorthand. Whatever we try to explain through an entire paragraph, that can be succinctly put using a simple formula. We are talking about the distribution of x bar or the sample mean. X bar follows normal distribution with a mean mu and standard deviation sigma by root n. So this is the heart of central limit theorem. Let's now look at the applications of central limit theorem. There are many applications of central limit theorem. One of the most famous and popular applications of central limit theorem is in hypothesis testing. I repeat, in hypothesis testing, central limit theorem finds a lot of application. Typically, central limit theorem is used to construct the confidence interval. Let me give you one real-time example of central limit theorem. Central limit theorem is useful in election polls. I'll repeat this for you. Central limit theorem is very, very useful in election polls. To calculate the percentage of persons supporting a particular candidate, which are seen on news as confidence intervals, we use central limit theorem. So these are the two major applications of central limit theorem. With this, I have come to the end of today's video. In today's video, we've seen one of the most important applications of central limit, one of the most important theorems in statistics. This important theorem is called as CLT or central limit theorem. We have seen the prerequisites for us to apply the central limit theorem. What is the ideal sample size for which central limit theorem can be applied? We have also seen the three important properties of central limit theorem. Further, we went on to discuss the applications of central limit theorem. I thank you very much for watching this particular video. I request you to subscribe to my channel, also like and share my videos. Thank you very much once again. Have a great day ahead.